Okay, now, take the y equals 2 to the x graph, or table, and switch columns. We get the y equals log base 2 of x function. This was done for homework, so everybody should be familiar with this. And the graphs of these two functions look like this, and everybody, I believe, would have gotten these graphs. Everybody did the homework. If you hadn't done the homework, again, let me put a plug in for doing the homework. If you haven't done the homework, you aren't up with what I'm saying here. Okay, so anyhow, so you got the function y equals f of x equals 2 to the x, that's this one, and right there's its graph, and y equals f inverse of x, which is a log base 2 of x, which is this one. Now this f inverse thing, that means the inverse function. If this is f of x, this is f inverse of x. Okay? And for any function, if you do this, you get the inverse relation, and if the relation is a function, you have an inverse function. If the relation isn't a function, well, you restrict the domain of this thing, and that gives you an inverse function on a restricted domain. But we'll talk about that in more detail soon enough. Okay, so here we have it. We also see that the coordinates switch. So if this is 1 here and this is 2 here, this would be 1 here, this would be 2 here. Scales aren't quite right. In other words, the point 1, 2 lies on the graph of the f of x function. The point 2, 1 lies on the graph of the inverse function, the log base 2 function, the f inverse of x function for this f of x function. And if we draw the little rectangle that indicates, well, the little rectangle formed by the projection lines from this point, if the scales are the same, you're going to get the same rectangle here, but flipped over and actually kind of reversed. And we'll talk about that a little bit later also. Okay, so we want to look at the property of inverse functions. The property is that if you do f of f inverse of a number, you get that number back. And similarly, you do f inverse of f of a number, you get that number. So here we do f of f inverse of 2, and we work that out and we get 2. Here we do f inverse of f of 2, we work that out, and again we get 2. Now let's look at the details of that. First of all, f of f inverse of 2. Well, f inverse of 2 would be the inverse function, the log base 2 function applied to 2. If x is 2, the inverse function gives us 1. Okay, so we have 2 here, which gives us 1. And that's what we get if we plug 2 into the inverse function. And then, of course, since f inverse of 2 is 1, we have f of 1. Now, how do we get f of 1? Well, here's our 1. And, of course, this 1 has to match this because the number here is what we got when we did this. Okay, so the 1 here kind of feeds back here, which then feeds over to the 2. And there we have it. Now, we don't have to draw those arrows or any of that. F inverse of 2 is 1 because that's what the table tells us. And then f of 1 equals 2 because that's what this table tells us. So those are the values that we get, and we see that f of f inverse of 2 has to equal 2. Anytime we do f of f inverse of some number up here, we're going to get the corresponding number in the y column. And then we're going to apply f to that, meaning we're going to take that same number, bring it back over here, and apply the f function, which has to give us the same value. You want to think through that if you don't totally understand it. Takes a little thinking. Okay, and then f inverse of f of 2. Well, we use the same thing, but we're doing f of 2. So we start with 2. And we get 4, which is our f of 2. So we can say x is 2. And now f inverse of f of x is f inverse of f of 2, which is f inverse of 4. Okay, so we get the 4 here, and from that we get the 2. It gets a little clumsy to label these, but I'll go ahead. So this is f of 2 is 4, and f inverse of f of 2 is f inverse of 4, which equals 2. So we start with 2, we end with 2. F inverse of f of 2 equals f inverse of 4 equals 2. Okay, this is the case for any value of x. Okay, you can see how it'll work out with the table, but that's the definition of the inverse function, and somehow I seem to have rushed out my, no I didn't, okay. Okay, so we have, for any inverse function, if f is a function, f is its inverse, f of f inverse of x equals f inverse of f of x equals x. That's the property of an inverse function. Okay, well, that can be useful. Okay, f inverse of f of x equals x. Well, what's our f of x function? Our f of x function is 2 to the x. What's our f inverse function? Well, we call that the log base 2 function. So, saying the same thing, f of x is 2 to the x, f inverse is a log base 2 function. We say that log base 2 of 2 to the x equals x. Okay. Again, that says, and another way of saying it is, well, the other condition for the inverse is that f of f inverse of x equals x. F inverse of x is the log base 2 function. F of the log base 2 function is 2 to the log base 2, because f of x is 2 to the x. F of f inverse of x would be 2 to the f inverse of x. F inverse of x is log base 2 of x, so it's 2 to the log base 2 of x, and that has to equal x. So we have these two facts for the log function, base 2 log function. And these facts are keystone facts for solving what we call logarithmic equations and exponential equations. Okay, here we have an exponential equation. 2 to the x equals 5. Well, how do we solve this equation? We solve it with the inverse function. 2 to the x equals 5, so log base 2 of 2 to the x will equal log base 2 of 5. Okay, we just apply the log base 2 to both sides. And there's a little more to it, but that's, you know, we have to be careful when we do that, but we can do it. So we'll see the special cases and so forth in a little while. But anyhow, taking this equation, applying the inverse of the 2 to the x function, what do we get? We get log base 2 of 2 to the x. Well, that's just the inverse function applied to the function. That's just going to give us x. And that's going to equal log base 2 of 5. Now, you might say at that stage, well, okay, but what in the world is log base 2 of 5? Well, there are two ways we can see the log base 2 of 5. One is to draw the graph of the base 2 log here and go out to where x equals 5 and find out what the x value or the y value is. That'd be the log base 2 of 5. Now, you could only do that by estimate, but you could, if you have a pretty good graph of the log base 2 function, you can do a pretty good estimate. So you get a fairly good estimate of what the log base 2 of 5 would be. Well, that's fine, but what if you want a more accurate value, because estimates are estimates? Expect your estimate to be close enough for imprecise more or less right, but not really precise calculations. We need to be able to evaluate this. Well, just like a square root, We don't have any good way of evaluating these things using arithmetic. There are ways, but it involves some higher mathematics, and they'd be very tedious, so nobody's going to do that. Okay? We used to know an algorithm for doing square roots, and that wasn't too bad, but nobody uses it because we have calculators. Okay, so then we have Taylor series, but you don't know about that. Okay, so we can use a calculator to do log base 2 of 5 by a simple rule for logarithms that the log to whatever base of a number is the log of that number divided by the log of the base. Base is 2, okay? So in the denominator you're going to have log 2, in the numerator you're going to have log 5. Now you can do this with a calculator because your calculator has a log key. Hopefully you've seen it before. If not, just look. Okay? And it also has a natural log key. It's an ln. And if you use ln, it's the same thing. You just use an ln for the numerator and the denominator. Whatever you do, don't use the log for one and the ln for the other. As long as you use the same one, it's okay. So, if you didn't understand that, just use the log key. We'll see more later. We'll see what the natural log is. We'll see why it's important. Okay, so there's your log key. Okay, now, if we want to solve the equation 2 to the x equals 5 using graphs, we know how to do a pretty accurate graph of the 2 to the x function. Now that graph only goes up to where x equals 2 and y equals 4. Of course, here are the points of our basic function. But we could extend on out a little bit to 5 if we kind of keep the trend of the curve going. It's getting steeper and steeper. So we can come up here to 5, and that would be the y value. That's y equals 2 to the x. So y equals 2 to the x function. So if y equals 5, we find the corresponding x value here, which looks to be about 2.4. It's a little high, I think. But there it is. It's closer to 2.2. I think I've punched it into a calculator. I've got other methods. Okay, so according to this graph, we get an estimate of 2.4. That would be a solution to 2 to the x equals 5. This says that 2 to the x has a value of 5 when x equals about 2.4. Now, if you do the log 5 over log 2, you're going to get something, I think, closer to 2.2, maybe as much as 2.3, but I think certainly no more than that, just looking at points on the graph. So this equation says what x value on the 2 to the x graph corresponds to y equals 5. And you want to understand the equation that way, and you also want to understand how to solve the equation using the inverse function, using the log base 2 function. So we say that the x value for which y equals 5 is the solution of the equation 2 to the x equals 5. Now that's the y value on the graph of 2 to the x. I did write all that up. Okay? Now one quick blurb that I just tossed in at the end of class. One reason this is really important is, let's say that you scrape up $2,000, decide to invest that, and keep it as long as you can to see how much money you can get. By the time you're my age, you hope maybe it grows to $2,000 and you go out and buy a good steak dinner. Okay, so let's say you invest the money at 3%. Now, without going into the details of how many times it's compounded and so forth, it turns out if it's compounded annually, then the amount at the end of t years will be 1.03 to the t. Well, it would be 2,000 times 1.03 to the t. The 3% is your 0.03, the 1 is your original principal, and t is the number of times you get to multiply by 1.03. And you don't have to understand that. We're going to do that a little more slowly very soon. Point is, this is very similar in form to this equation. You got a t in the numerator instead of an x, and you got a 1.03 instead of a 2. And you got something in front of this rather than just having a number over here. But you can solve it very easily using something very similar to what we did here. First place, you want something to some power to equal some number. You don't want anything in front of it. So you divide both sides by the 2,000. Then you get 1.03 to the t equals 5. And now it's looking a whole lot like this. You've even got the 5 there. Okay? Now you got a t instead of an x, and you got a 1.03 instead of a 2. Well, all you do here then is you take log base 1.03 of both sides. Instead of taking log base 2, the base of your exponential, instead of being 2, is 1.03. So you take the log of both sides, and the log base 1.03 is inverse to the 1.03 to the t function. So you're just going to get t here. And that gives you then log base 1.03 of 5. Well, how do you do log base 1.03 of 5? You go to your calculator, because you don't have a good graph of 1.03 to the t. You go to your calculator, you do log 5 over log of 1.03, and you find out how many years it's going to take. That's all. And this is fundamental to finance, this idea of interest and exponential growth of principal is just absolutely keystone fundamental in personal finance. You handle your money for the rest of your life, and in, of course, higher finance. So you're unlikely to be working with the mathematics of higher finance, except as it applies to you personally, but it's really important to know this sort of thing. So that's one use of this, and there are many, many others, and we'll talk about some of them. Okay, so that's just a quick introduction to logarithmic functions and how they might be used, how logarithmic equations are solved, and some important, at least one important type of application.